Okay. Let me just briefly welcome all the members. Good morning and welcome to all the KPA members and other invitees to this online webinar today. So, Raichur Professor Dr. Sharanbasava Khened he is going to talk about SLAC, his visit to SLAC. SLAC last month visit ಮಾಡಿದ್ದಾರೆ ಅದರ ಬಗ್ಗೆ ಅವರು ಮಾತಾಡ್ತಾರೆ. ಸೊ ನಿಮ್ಗೆ ತಿಳಿದ ಹಾಗೆ ನಾವು 1.5 ವರ್ಷದಿಂದ ಈ ಆನ್ಲೈನ್ ವೆಬಿನಾರ್ ಸೀರೀಸ್ ಮಾಡ್ಕೊಂಡು ಬರ್ತಾ ಇದ್ದೀವಿ. ಸೊ ನಮ್ಮ ಮುಖ್ಯ ಉದ್ದೇಶ ಏನು ಅಂತ ಹೇಳಿದ್ರೆ ಟೀಚರ್ಸ್ಗೆ ಇನ್ ದ ಮೋಸ್ಟ್ ಕಂಫರ್ಟಬಲ್ ಮ್ಯಾನರ್ ಅವ್ರ ಮನೆಗೆ ನಾವು ಬೇರೆ ಬೇರೆ ವಿಷಯಗಳನ್ನ ಅಟ್ಲೀಸ್ಟ್ ಇನ್ನು ಸಿಂಪಲ್ ಆಗಿ ಮುಟ್ಟಿಸ್ಬೇಕು ಅನ್ನೋ ಉದ್ದೇಶ. ಸೊ ಎಜುಕೇಶನ್ ಥ್ರೂ ದಿಸ್ ಆನ್ಲೈನ್ ಮೋಡ್ ಬಹಳ ಕನ್ವೀನಿಯಂಟ್ ಆಗುತ್ತೆ, ಮತ್ತೆ ಕಾಸ್ಟ್ ವೆರಿ ಲೀಸ್ಟ್ ಅಮೌಂಟ್ ಆಫ್ ಕಾಸ್ಟ್ ಇರುತ್ತೆ. ಆದ್ರಿಂದ ಇದನ್ನ ನಾವು ಫಾಲೋ ಮಾಡ್ತಾ ಇದ್ದೀವಿ. ನಮಗೆ ಎಲ್ಲ ತರದ ಕಾಲೇಜು, ಯೂನಿವರ್ಸಿಟಿ ಮತ್ತು ರಿಸರ್ಚ್ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಇರುವಂತ ಸೈಂಟಿಸ್ಟ್ಗಳು ನಮಗೆ ಸಹಾಯ ಮಾಡ್ತಾ ಬಂದಿದ್ದಾರೆ. ಅವ್ರಿಗೆಲ್ಲ ನಾವು ಋಣಿಯಾಗಿದ್ದೇವೆ. ಸೊ ನಮ್ಮ ಉದ್ದೇಶ ಈಡೇರ್ಬೇಕಂತ ಹೇಳಿದ್ರೆ ತಾವೆಲ್ಲ ಭಾಗವಹಿಸ್ಬೇಕು, ವಿದ್ಯಾರ್ಥಿಗಳು ಮುಂದೆ ಬರಬೇಕು, ಮತ್ತೆ ಚರ್ಚೆಗಳು ಮಾಡಬೇಕು. ಈ ರೀತಿ ಸೈನ್ಸ್ ಬೆಳಿಬೇಕಂತ ಹೇಳಿದ್ರೆ ಚರ್ಚೆಗಳಾಗಬೇಕು, ಪ್ರಶ್ನೆಗಳು ಹೇಳ್ಬೇಕು, ಈ ತರ ಡಿಸ್ಕಷನ್ ಆಗಬೇಕು. ಇಟ್ ಇಸ್ ನಾಟ್ ಒನ್ ಮ್ಯಾನ್ ಸೈನ್ಸ್, ಒನ್ ಮ್ಯಾನ್ ಸಬ್ಜೆಕ್ಟ್ ಅಲ್ಲ. ಫಿಲಾಸಫಿ ರಿಲಿಜನ್ ಆದ್ರೆ ಒನ್ ಮ್ಯಾನ್ ಸೈನ್ಸ್ ಆಗ್ಬಿಡುತ್ತೆ. ಇದು ಪಬ್ಲಿಕ್ ನಾಲೆಡ್ಜ್ ಆಗಿರೋದ್ರಿಂದ ಸೈನ್ಸು ಇಟ್ ಡೆವಲಪ್ಸ್ ಥ್ರೂ ಇಂಟರಾಕ್ಷನ್, ಕ್ವೆಶ್ಚನ್ಸ್, ಆನ್ಸರ್ಸ್ ಅಂಡ್ ಥಿಂಕಿಂಗ್, ಕಲೆಕ್ಟಿವ್ ಥಿಂಕಿಂಗ್. ಓಕೆ, ಈ ದೃಷ್ಟಿಯಿಂದ ನಾವು ಇದನ್ನ ಮಾಡ್ತಾ ಇದ್ದೀವಿ. ಸೊ ನೀವೆಲ್ಲರೂ ಕೂಡ ಭಾಗವಹಿಸಿ ಮತ್ತು ಯಾವುದೇ ಒಂದು ವಿಷಯದ ಬಗ್ಗೆ ಮಾತಾಡೋದಕ್ಕೆ ರೆಡಿ ಆಗಿರಿ. ವಾರ ನಾವು ಮಾಡ್ತಾ ಇದ್ದೀವಿ. ಅಂಡ್ ವಿ ಆರ್ ವೆರಿ ಥ್ಯಾಂಕ್ಫುಲ್ ಟು ಡಾಕ್ಟರ್ ರಾಘವೇಂದ್ರ ಫಾರ್ ಪ್ರೊವೈಡಿಂಗ್ ದಿ ಲಿಂಕ್. ಸೊ ಇಷ್ಟು ಹೇಳಿ ಇವತ್ತಿನ ಕಾರ್ಯಕ್ರಮದ ಬಗ್ಗೆ ಇವರ ವ್ಯಕ್ತಿ, ಈ ಸ್ಪೀಕರ್ ಬಗ್ಗೆ ಒಂದು ಸ್ವಲ್ಪ ಬ್ರೀಫ್ ಆಗಿ ತಮಗೆ ಪರಿಚಯ ಮಾಡ್ಕೊಳ್ತಾ ಇದ್ದೀನಿ. ಡಾಕ್ಟರ್ ಶರಣಬಸವ ಖೆನೇದ್ is retired principal and associate professor of physics, NVD College, Raichur. He served there for 38 years. He did his MSc from Karnataka University in 1979 and joined NVD College as a lecturer in physics. He got UGC teacher fellowship and did his research work leading to PhD degree from Rama Research Institute, Bangalore, under the guidance of Professor S. Chandrasekhar. Liquid crystals professor.
ಇದು ಕಳಿಸಿ ನೋಡ್ರು ಲಿಂಕ್ ಹೊಸದಾಗಿ ಆ ಲಿಂಕ್
His research was on physical properties.
ಬರ್ತದೆ ಇದನ್ನ ಕ್ಯಾನ್ಸಲ್
ಬಿಟ್ಬಿಡಿ, ಇವಾಗ ಮಾಡ್ಕೋತಾರೆ ಬಿಡಿ, ಪ್ಲೀಸ್ ಡೋಂಟ್. Physical properties of liquid crystals. Electrical properties of ferroelectric liquid crystals under high pressure. He has authored 25 peer-reviewed articles in international journals and co-authored a chapter in a World Scientific published book titled Modern Topics in Liquid Crystals. He has presented his research work in 3 international conferences and more than 25 national conferences. He has guided 3 students to MPhil and co-guided 2 students with PhD degree. Dr. Khened was a member of Academic Council of Gulbarga University, chairman of the Board of Examiners of Gulbarga University, and also a member of the Board of Examiners of Bangalore University. He has served in various capacities. He is a member of the elite panel of the Department of Science and Technology, Government of India for the INSPIRE program. He has served as a member of the Zonal Advisory Board, LIC of India, Secunderabad. He was the founder, coordinator of the Raichur Source Data Management System of Karnataka State Council for Science and Technology. He was a member of the selection committee for assistant professors in physics at the University of Agriculture Science, Raichur. He has written a very large number of popular science articles and has delivered a large number of radio talks on various subjects in Kannada. So we are indeed very fortunate that he has agreed to give a talk on his experiences on his visit to SLAC, which is in USA, Canada. In California, USA. So over to Dr. Khened for his presentation. You can please continue. Take over. Dr. Khened, you can speak. If my mute agbitre, mute microphone silent agide, microphone on ಮಾಡ್ಕೊಳ್ಳಿ. Mute ಆಗಿದೆ ನೋಡಿ. Unmute. Microphone. Mute ಆಗ್ಬಿಟ್ಟಿದೆ. ವಾಯ್ಸ್ ಬರ್ತಾ ಇಲ್ಲ, ಮ್ಯೂಟ್ ಮೈಕ್ರೋಫೋನ್ ಮ್ಯೂಟ್ ಆಗಿದೆ. ಪ್ರೊಫೆಸರ್ ಖೆನದ್ ಲೆಫ್ಟ್ ಸೈಡ್ ಇರುತ್ತೆ, ಲೆಫ್ಟ್ ಕಾರ್ನರ್ ಇದು ಮೈಕ್ರೋಫೋನ್ ಇದನ್ನ ಓಪನ್ ಮಾಡ್ಕೊಳ್ಳಿ. Zoom left side microphone ಇದೆ ನೋಡಿ, ಸಿಂಬಲ್ ಇದೆಯಲ್ಲ ಅದು ಕ್ಲೋಸ್ ಆಗ್ಬಿಟ್ಟಿದೆ. Microphone, please open the microphone. Unmute.
ಏನ್ ಬರ್ತದ
Okay, now it's good. Okay, ಮಾತಾಡಿ. Okay. ಮೊದಲಿಂದ ಹೋಗಿ next previous side.
ರೈಟ್.
Please go on. ಮಾತಾಡ್ಬೋದು ಇವಾಗ.
ರೈಟ್ ರೈಟ್. ಚೈತನ್ಯ ಇದು ಬರೋಲ್ಲ.
ಬರ್ತಾ ಇದೆ ಮಾತಾಡಿ ಈಗ. ಬರ್ತಾ ಇದೆ.
ರೈಟ್. ಗುಡ್ ಮಾರ್ನಿಂಗ್ ಫ್ರೆಂಡ್ಸ್.
Good morning, Kenneth.
ಹಲೋ, ವೆರಿ ಗುಡ್ ಮಾರ್ನಿಂಗ್.
And Kagli, sir.
ಆಮೇಲೆ ಮಾತಾಡೋಣ ಸರ್. ಈಗ ಶುರು ಆಗಿದೆ, ಟಾಕ್ ಶುರು ಆಗಿದೆ, ಆಮೇಲೆ ಮಾತಾಡೋಣ ಮುಗಿದ್ಮೇಲೆ. ಓಕೆ ಸರ್, ಮಾತಾಡಿ.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. It's amazing to speak to you all from here. Today's talk is a result of my visit to SLAC. So because of my son moving to USA, I happen to visit him every year because of my grandchildren. Knowing my interest, he has taken me to premier educational institutions of USA like Stanford University, Berkeley University, MIT, Harvard University, California Institute of Technology, etc. This year, he has taken me to SLAC. And while fixing Dr. Ashit's talk last time, I just mentioned Professor Kagle that I am visiting SLAC. Immediately he told me that you have to give a presentation on your visit. So that is, this talk is the result of that. So that's why I am here to speak to you about my experience in the SLAC. Okay, and please note that this is a right, no problem. Okay, only a visitor's view, not because I did not do any experiment there. Anyway, SLAC is a National Accelerator Laboratory operated by Stanford University for the US Department of Energy. Okay, and as I had already told you, so this actually my talk covers overview of its history of SLAC, major facilities, recent technological upgrades, and groundbreaking scientific results. I don't know.
Previous, back.
Okay, yeah.
Forward. Okay.
So here to visit SLAC, we have to take the permission online, and we should go there. So this is the SLAC center, science SLAC science and user support building. So we have to report here. So when we report here, so we can sit there, and actually they have put so many their diagrams, etc. Whatever they have done, we can be seeing that. They immediately they will call us. They will take us to a meeting room, and there they present an audio-visual presentation. In that, they give information about the history and how it's working, and also what are the great works results they have taken, and what are the there's slightly some 8 to 10 minutes presentation they give. So based on that only I am giving you. So this SLAC history, this is very interesting. Actually, this idea of you all know that because all our physics professors, it's a linear accelerator. It is the longest accelerator in the world, around 2 miles. It's a 2-mile linear accelerator situated in Stanford University. Actually, the idea came in 1956. It was proposed in 57, and the US Congress has authorized it, and the work started. Initially, this was called as Project M, the monster, because it is 2 miles. That's why they called it as monster. So again, in 1960, they called this. They did not feel that Project M is not good. So that's why they called it as the Stanford Linear Accelerator Center. That's why it's called a SLAC, so Stanford Linear Accelerator Center, from August 1960. Again, in 2000 something, I think, 2008, they called it as a SLAC National Accelerator Laboratory. So the construction began in 1962 and completed in 1966. So according to the statistics, they say that the cost of this project was $114 million on that day. According to them, on this day it is 1 million or slightly more, maybe around, in Indian, maybe it is around 10,000 crores. So he is Professor W.K.H. Panofsky. He is the founder director, and he is responsible for the construction of this, etc. So see his ideas. He said, in high energy physics, you have to have bigger and bigger instrument to see smaller and smaller things. So such a big 2 mile accelerator is required to see very small minor things like elementary particles. So that was his view. So accordingly, they built it. So this 3.2 kilometer accelerator tube was placed 30 feet below. So because why actually we keep that, they have kept it below means that is, they say that this is safety point of view, environmental concern, operation, integration, and it's also effective shielding from radiation, etc. So minimum pollution, it enhances structural stability, improves functionality while utilizing surface land. The land also can be utilized, okay. So here below the ground, they have this 2 mile accelerator pipe. Above, they put this clusterons, which generate microwave, and they accelerate the particles. So this is the groundwork. Actually, these are I've taken from them because they show this. See how they worked. Also, so many workers were there, etc. So, and you see, 1962 only that they are planning that future highway, and this was built below that. This is the accelerator, linear accelerator. You can see that. So you can see this is 2 mile accelerator, linear accelerator, and this is the Stanford University campus. Now this is clearly visible now. So from here, yeah. And interestingly, while they were digging, they found this skeleton. And accidentally, the wife of Professor Panofsky, she was a paleontologist, and she found interested in this, and she found that this is actually 8 to 12 million old, some Nepodoxia repanengi, this is a marine mammal, like so sea elephant or something like that, you can say. Okay. And next, what they do after the show, they will take us in a bus to the point. So here you can see this is the building, 2 mile. This is very 2 mile building. So on top of this, this is the on the ground. On the ground, you can see this. Below the ground, again I'll show you. This below the ground, we can see this. This is a so this below the ground, you see the accelerator pipe, and on the ground, you see this building. Inside this building, you have this clusterons. These clusterons, they actually produce they are operated with radio frequency. Yes.
No, please go on. Some disturbance. Okay, please go on. No problem.
Okay. So in the from the clusteron, they actually accelerate the electrons using microwaves. 2560 megahertz microwave they use to accelerate these electrons. And you have this cooling, etc. This is the old one. Now the first one what I have shown is that's a new one. This is a old one they are using. That's a now they have used. That is purely 99.9% copper tube, 2 miles. So how it operates? So the electrons are injected to the accelerator, and the electrons are accelerated precisely in the pipe. There are machined cavities are there. They are actually radio frequency cavities. They call RF cavities. In the RF cavities are powered by the clusteron which generates millions of watts of microwave power. So because of that, the electrons get accelerated, and they see that the electrons enter into a particular cavity exactly when it gets accelerated. So that's how along the length again they keep thousands of magnets to keep the electrons focused so that they should move in a single line. They should not spread. So in spite of that, there are some actually some losses there, but to prevent losses from if so, that's why usually there is maintain a very high very low pressure, so that no atmospheric molecules, etc., gas molecules, etc., are there, so that the electrons won't lose any energy. So that's why inside the tube, ultra vacuum is maintained to electrons from colliding with air molecules. Okay, so this accelerated beam from the linear accelerator, linear accelerator, at the end, it's directed and it goes to different experimental areas where experiments are done. So sophisticated electronic system is used for controlling. So these are some of the, actually they show us, these are the photos taken by me. So some electronic, but they show us and not many people there. Some people are working, they won't talk. And some people, they also explain us. This is the what, that's what they are doing. So these are another, this one, this is another one. So this is that mic, this ultra vacuum instrument. This is ultra vacuum instrument which they use to maintain that. Okay, and even if you ask some question, there will be some persons, but unfortunately what happens, you see, this is such a huge accelerator and lot many works are being going on. So some people, for example, she knows about a big, there is one telescope is being set up. She knows more about the that telescope, etc. She can tell more, but less about this. But in spite of that, they so little things and they explained. So initially, so what happens? You see, these electrons, they are made to move in a, we call the sphere. This sphere is stand for positron electron acceleration ring. So in that ring, the particles are enter and they will be moving. So what they do is, because positron and electrons are moving in different directions, they see that at some particular point they move along same straight line and they collide. So there they have kept some very sophisticated instruments and they study that. They detect the collisions and they study the effect of that. So from 1966 to 1976, so actually such a huge 3.2 kilometer along this one, the building was built and all the equipment, etc., everything that work, everything was done in 2 years only. They could do it. From 66 onward, they started doing work. And between 66 and 76, whatever work they have done on this basic first thing, they got 4 Nobel Prizes. So which just I'll explain about these Nobel Prizes. So because we physics people, we know that the, and what I have told is the work done was that time, but Nobel Prize they got later on. For example, one prize in 1976. In 1976, this Burton Richter, he is from SLAC, and also another person from MIT. They discovered J and psi. This is a heavy elementary particle like J and why is this J and psi means this Burton called this as psi particle and Samuel Ting called it a J particle. Therefore, this they together they say J psi particle, a heavy elementary particle, and the existence of charm quarks. So they got the prize, Nobel Prize in 1976. Again, in 1919, Nobel Prize is got by this Richard E. Taylor SLAC. And but all of them, they did experiment here only. So deep inelastic scattering of electrons on protons and bound neutrons. So this particular experiment is very, very important because this confirmed the existence of quarks and also standard model. So this gave, and of course, afterwards only the charm particle was discovered, but they were given Nobel Prize first, and these people were given later on because this involved standard model, etc. Maybe that's the reason. So quarks. Actually, there they got charm quarks in the first, and here they got up and down. It's top and bottom quark particles in the second experiment. Again, in 1995, Nobel Prize is got by Martin Perl. He won for the discovery of tau lepton, a heavier cousin of electron. This is around 3,500 times heavier than electron, tau lepton. So this lepton is very difficult to. Yes.
No, continue. Some people are
Okay.
talking.
Oh, okay. So this is
ಹಲೋ
very.
ನಿತಿನ ಏನ್ ಮಾಡಕ್ಕೆ
This is very, very, because leptons, it's very difficult to identify them and find them. So that's why he got the Nobel Prize. Again, in 2006, Nobel Prize is got by in chemistry by Roger Kornberg. He was awarded for his studies. He said that the DNA's genetic blueprint in producing the protons, DNA genetic blueprint is there. He did that experiment and he told that protein development is based on DNA's genetic blueprint. So he got the Nobel Prize in 2006. These 4 Nobel Prizes were got by these people in the first 10 years only. So, for example, separately I got this man is Burton Richter, and he got the first one, and these 3 people. The second one, what I told, and this is Martin Perl. In fact, Martin Perl was also the director of SLAC later on after Panofsky, and he is a chemist. DNA genetic blueprint. That's what he said. Okay. Next. So afterwards, see, people were actually interested in finding Higgs boson, etc. By that time, that CERN was coming into existence, and some other accelerators were also there. Therefore, elementary particle study, interest in elementary particle study is reduced now. So, but see the interesting thing, because people got less interest in elementary particle study here, what they did, they have changed their direction of research. In the sense, what they did, so they started using these accelerated electrons to produce high energy X-rays, and they started studying high energy X-rays. Further, with some improvements, they could get X-ray lasers, so which are very, very powerful, intense, as intense as 10 power 9 times intense X-rays than the usual X-rays they got. So because of this high intensity, they could get better, very good results in different fields. So that's what I say. What was very interesting, what appeared very interesting for me in SLAC is that, see, in our laboratories, what we do is, we know the professor comes and he is interested in a particular instrument, he gets it, he does with his students, the people. Once the professor retires, that instrument is gone. Nobody else is interested, and they don't want to renovate that or use it for any other purpose. But here, what they have done, you see, because they invested so much money, they started using for different other purpose, and you see how effectively they use it. Means now SLAC is research is done in SLAC in all the fields. That's what I liked it. Okay, so from 80s onwards, SLAC is used as the source of strong X-ray radiation, as I told you. So these are different. This one first, initially it is Stanford Synchrotron Radiation Project. Okay, here, as I told you, they use one storage ring. I'll explain that about the storage ring once. That means actually they accelerate the electrons and in such a way that a bunch of electrons together will attain some particular velocity. How do they achieve this? Means actually by adjusting the microwaves. They adjust the microwaves in such a way that if a particular electron is very, very moving fast, means that will be accelerated less in the cycle of that microwave, and the electron which is coming slow, that gets accelerated more because of the sine waves. So they adjust it such that you get a bunch of electrons. And because of bunch of electrons are there, so if one electron, they get, so they deviate one electron and get X-rays. So if one electron emits X-ray, then all the other electrons in that bunch will have the same phase, and hence you have the something like lasers. So that is linear coherent light source. Okay, and LC, this is the first they had this linear coherent light source LCLS, and recently what they have done, they have upgraded this LCLS2. And this is very recently they started work. Actually, they started working from 2024 only on this. This gives again very powerful X-ray lasers. So and so accordingly they changed this the instruments also. That's why you have got facility for, that is facet 2, facility for advanced accelerator experimental tests. So this is LCLS. They have got different this one. So linear current this light source LCLS, the first one. So world's first hard X-ray free electron laser. Now this is the sphere what I am telling. So actually you see this, you can see the first one, this, the electrons enter into this sphere. They will be moving in a circular path. Actually they have also shown this, they have taken this diagram and they have shown this. This is very nice. You can see the path of the electrons here. They will be moving here, and somewhere they put some magnets, and they, because of that, they get diverted and they go away, and they enter into different experimental setups, and people use those things. And even the another interesting point is that the electrons which are not being used, so because you cannot use all the electrons, so their energy is again they take back, and they again they use this for some other purpose. That's a very interesting aspect of this. Okay, so this X-ray lasers are produced by SASE, that is self-amplified spontaneous emission. As I have explained, that is because of this bunching. In the bunching, when one electron produces X-ray means, so that will, the others will also follow, they have the same coherence. So that's why you get X-rays. So this is, as I told you, something is there 10 power 9 times more brighter than the usual X-rays, and their energy range from 10 to 20 kilo electron volt. That is sufficient for one. Okay, so then once you get the X-rays, generated X-ray is then directed to beam lines for various experiments. They have a beam line. Different people will use the beam line some for different experiments. So experiments like X-ray crystallography, X-ray absorption spectroscopy, X-ray scattering, etc. They use this. Okay, so because of this X-ray laser its unique properties allow scientists to study the materials at the atomic level with unprecedented precision. So this radiation is cornerstone in fields like medicine, environmental science, and material research. So these are different buildings wherein you have got different equipments, and they do different studies. So this you can have the clear picture of this. These are all. So that's what they say. Even though they spent $114 million for the for LINAC, for linear accelerator purpose, for all the other equipments, etc., at that time they spent around $80 million. So this is again, you can find these are all the different laboratories. It starts from this side, and this is the end point. Okay, so this is Stanford synchrotron radiation. That means this electron, whatever energy we are getting radiation from the electrons, accelerated electrons they emit, no, that's usually called a synchrotron radiation light source. So they have got the structure, they study structural biology, material science, environmental science, chemistry, and catalysis. So they apply this in medicine, technology, energy, etc. So I'll explain some things here. Sorry. Okay. So actually this is called a X-ray free electron lasers, because individual electrons are accelerated and individual electrons are diverted. So because the accelerated electron emits energy individually, so that's why this is a free electron lasers, they say that. This, okay. They have different studies like atomic structure studies, biology and medicine, etc. I'll come to the result. Nanomaterials, even they study quantum materials, quantum computing research. They are studying this in solar. For example, solar, they have, actually, I still remember that when we were teaching, we say that if the solar cells give 10% efficiency, then that is sufficient. We don't need any more other power sources like that. But now they have already achieved 25%, and which is commercially they are available now. But they say that they are getting as high as 47%. They reported 47% efficiency in solar cells in Stanford University. Okay, so now this is a clear picture. You can see that. So different, this one in 1962 what they are doing, and in 2023 presently what they are doing. Okay, so this is again this enhanced 2-mile LINAC upgrades to a higher energy and a better performance. So electron positron collisions only they are studying now. Along with that, they have got different studies. So the earlier fundamental particles only was there. Now along with fundamental particles, material science, biology, and advanced techniques, etc. Now they are using that. So you can see these key facilities. These are the facilities like LCLS, that's LINAC coherent light sources, etc. And then main experiments. Earlier they were only interested in elementary particles. Now it has been changed. Okay, so I'll come to the fine. This one. These are the different fields now presently they are using. X-ray and ultra-fast science. So because they are getting very high energy X-rays and ultra fast, because the electrons here are accelerated to 0.99996 they have reached 6.999 and 6 times the velocity of light they have reached. So ultra fast. So at that speed, the electron will be having some. They expect that you should have some 20 GeV, but it's not actually 20. They say that around 17 GeV they could get now. So therefore they could get more information. And X-rays, because of brightness is very large, even smaller things scattering. Actually, in scattering, the scattered light intensity is more important. So if the initial intensity is more, scattered light intensity will be better. So here initial intensity is 10 billion times more. Therefore, naturally scattered intensity is very good, and hence they could study the things very, very well. So another is physics of the universe. So this I'll tell later on. I'll come to that. Then advanced accelerators. Now you see, because this is an accelerator, then they started studying how effectively they can one can make very simple. Now they say that they have reduced the length by 10 times. Instead of 3 miles, you can within 0.3 miles. So accelerator only you can produce so much. They are doing that advanced accelerators also. Science of life, biologically, how one can use this. That is, they have studied protein, etc. And then new technologies like AI, quantum computing, etc., etc. And energy sciences. Energy science like what I had already discussed, that is solar cells, etc. And even batteries. Okay, I'll come to that. So this is actually the Kilpak. This is a unit wherein this is the physics of the universe dark matter. So physicists assume that actually what we are seeing is only 15%. 85% is still dark matter. We are unable to see that. People are they are and they are trying to find this dark matter, detect this dark matter, and they have done some experiments. I'll come to that. I'll show that. Okay, so here this is the one, Lux Zeppelin experiment. This is a cutting edge experiment. So this is actually used to determine the dark matter. Dark matter, so this makes up a large portion of the answer, and they won't interact with the light. That's why we call it as dark matter. So this Lux Zeppelin experiment, so what they have made a large tank filled with liquid xenon, and this is based on weakly interacting massive particles interaction. So because of that, tiny flashes of xenon is produced because of the release of electrons. So that can be detected. They kept this 4,850 feet below the Stanford. This is not a Stanford. This is Sanford, which is in South Dakota. Below that, therefore, only special radiation will only come and no other disturbances will be there. So that's how they are doing this. So I'll show you. So this is the overall experiment, and this is the Lux Zeppelin tube. So this is something like this is filled with xenon, and inside this 1 mile below they have kept it, and so what they are studying this, they are finding they are detecting the dark matter using this. And another is very interesting is LSST, the Legacy Survey of Space and Time Camera. So we all talk of where if I have a camera means what megapixel we call, but this SLAC people have designed a camera with 3.2 gigapixel, very sensitive 3.2 gigapixel, and very large one, something like 3 meter radius kind of thing, such a huge this one they have done. So therefore that can accumulate more and more information. So they have kept this LLST camera in Virasi Rubin Observatory in Chile. Okay, so there in they survey the southern sky, and providing unprecedented, because they are trying to collect data for 10 years continuously, and unprecedented amount of data is there. So this is actually, you can see the first figure, you can see all the rings, that is they are all the lenses, and this on this is this is the camera, which they are such a huge camera, they are lifting it here, and they have actually mounted this on top of a hill, and this is placed here, and this is actually this one, they rotate and they collect this. They say that continuously they collect it for 10 years, and then they study the fundamental questions of including nature of dark matter, dark energy, etc. They say that even they have got some results also, but this has been recently set up there, but still they say that they have got some results. And what all the future in what future directions, I think do you have time, sir?
Yeah, certainly. 10 more minutes. 10 minutes. No problem. Time is available. No problem.
Okay. So there in quantum research. So this SLAC is expected to play pivotal in development of quantum computing, because you see they have got very high power X-rays. They can study inside the atoms, how atoms are put inside the crystals, etc., how they behave, etc. Because of that reason only, this quantum dots, etc., they are studying on that. And then of course this LCLS is improved X-rays, they are getting better X-rays. So dark matter I have explained already. Even that they are using this for environment purpose, molecular biology, how actually they are using. So yes, see, next generation microelectronics, energy efficient microelectronics, even this quantum information, SL is actually in quantum computing and quantum sensing. And then fusion energy, they are even studying, trying to find fusion at lower temperatures. They say that they have succeeded, but still technology is not fully practicable. That's what they are trying to build up things. And machine learning and AI, see what happened, these people, they were using lot many computers, they were addressing lot many data. Because of using lot many computers and processing the data, so they became expert, and that's why they started working, some people started working on machine learning and AI for scientific discoveries, how one can use AI is for scientific discovery, etc. They started working on that. And of course advanced X-ray, and that I already told you. So now this is the finally this is SLAC at a glance. So this is SLAC is working with 6 joint research centers. There are different 6 joint research centers are there. Different centers are doing different works, and they see these lasers, there are as many millionth of a billionth of a second. That means so small, in a small time they are getting. That means in a second you get billions of pulses of X-rays. So that's why they could do whatever experiment they want, kind of thing it is. So that's it. They have given what are the important things about this stack at a glance. Of course, all these things I have taken directly from this one. They have given some pamphlets also. From pamphlets only I have taken, and as I have put it. So that is 10,000 times brighter, etc., faster, and then okay. And the SLAC is responsible for the beginning, the began meeting. SLAC auditorium helped this one. And in 1991, they opened the first website in the North America. They were the first to open the websites in that. And if we see the numbers, you see in 1962, there were only 200 employees. Now there are around 2,000, let us say, and then 300 postdocs and graduates are there. Thousands of researchers around the world, they are working. Even anybody, even in India also, people want to work, means they can apply there that we want to do this particular work, etc. They should get, and they will, if they feel that whatever work you want to do is good, they will help you how to get this visa, etc., and they will make all the arrangements. So those provisions are also there. Even some professor wants to visit that along with the students, mean they have got what I have. This is a ordinary visitor, as an ordinary visitor I had gone, but as a professor and with students you go, means separately each and everything they will take you to each and every part of it, and they will explain very nicely. And you can also then you get interested and do work in a different fields like that. That's what is they say. So actually this uses 426 acre of Stanford University area. Single SLAC, Stanford University has given 426 acre land for only SLAC. How much big should be Stanford University? They say the area of Stanford University is more than 8,000 acres. And as I told you, electron is 99.999 and 6/9% of the speed of light they get. And how much energy an electron gets means, as I told you, it is around 16, 17 giga electron volt. Or this is same as 33 billion AA batteries. If you keep 33 billion AA batteries together, how much power you get, that much energy a single electron gains from that. That's what they say. As many as 180 universities and research institutes make use of this, and 20 companies use X-ray facilities for research and aimed at developing medicines and other products. In conclusion, in the visit, so SLAC provides the world's leading research facilities and has contributed significantly for advancement of this one. And groundbreaking work in particle physics, material science, and photon science is commendable. It gives a strong emphasis on education and collaboration. Therefore, anybody interested, they can collaborate with that. So whatever I have seen and whatever little knowledge I have gained, that's what I am sharing, because I have not done any particular expert. I'm not an expert in that. But anyway, this is my experience. I felt that the most important thing is because they discovered some elementary particles and they got Nobel Prize, they did not stop it. That they converted the linear accelerator itself into other source, X-ray source, etc., etc., and they changed their ways of thinking and experiment. They are doing different experiments, and really it's commendable. What I feel, that's where we lag. So whatever facilities are there, we keep those facilities only for that particular experiment purpose. We should also think of the things. Then definitely we too can achieve the things. I uh, I profusely thank SLAC for providing me an opportunity to visit, and they helped me to explore its different aspects. And I thank Professor Kagle sir and all of you for patient listening. Thank you all. Thank you very much. If
Thank
you
you.
have any questions, of course, which if I know, definitely I'll answer.
Okay. If there are any questions, you may raise your hand. One question is already there. Professor Rudraswamy wants to ask you a question. Rudraswamy ಅವರೇ ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಳ್ಳಿ, ನಿಮ್ಮ ಮೈಕ್ರೋಫೋನ್ ಮ್ಯೂಟ್ ಆಗಿದೆ. Rudraswamy, unmute your microphone. Okay.
Yes. Congratulations, sir, Professor Kenneth, for sharing your information on SLAC. It was exciting to know more about SLAC. I have two questions, sir, basic questions. Does funding entirely come from US government? And second question, does LINAC uses to accelerate only electrons, or does it possible with other ions? These are the two questions.
Yes, sir. You can accelerate other also. They are doing electron, positron acceleration, electron acceleration. They are doing it. But it should be, because it's a LINAC, it should be a charged particle. That's all. Any charged particle is okay. That's number one. And another is funding. Actually, they have got a lot of collaborations. They have got a lot of patents, and they work with so many. Here in US, all the universities, they have got sponsors, other sponsors, because they utilize their research facilities there and patents, etc. They earn a lot of money. I think recently you may be knowing, Harvard University people rejected government funds. They say that we are happy with our funds. That's how they are getting a lot of. That's what they said. Some 20 companies are running with it.
Okay.
Will be sponsoring research work. Companies sponsor ಮಾಡ್ತಾ ಇರ್ತಾರೆ.
Yes, ಕಂಪನಿ ಅವ್ರು ಮಾಡ್ತಾರೆ ಸರ್. ಹಿಂಗಾಗಿ ಅವರಿಗೆ ಇಲ್ಲಿ ಯಾರು ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ನವ್ರಿಗೆ ಅವ್ರಿಗೆ ಅಷ್ಟು ಫಂಡ್ಸ್ ಏನು ಪ್ರಾಬ್ಲಮ್ ಇಲ್ಲ ಅಂತ. ಬಟ್ ಅವರೆಲ್ಲರಿಗೂ ರಿಸರ್ಚ್ ತಾವು ಪ್ರಾಜೆಕ್ಟ್ ಬರೋದು ಇದನ್ನ ಮಾಡಿ ದೇ ಗೆಟ್ ಮನಿ.
ಪ್ರೈವೇಟ್ ಗ್ರಾಂಟ್ಸ್
ಪ್ರೈವೇಟ್ ಗ್ರಾಂಟ್ಸ್ ಭಾಳ ಇರ್ತದೆ ಸರ್.
Can I add something here, sir?
ಹೇಳಿ ಸರ್.
ಮೊನ್ನೆ ಓದ್ತಾ ಇದ್ದೆ, ಈ ಹಾರ್ವರ್ಡ್ ಯೂನಿವರ್ಸಿಟಿಗೆ $53 ಬಿಲಿಯನ್ ಬರುತ್ತಂತೆ ಎವ್ರಿ ಇಯರ್ ಹೆಲ್ಪ್.
ಅದಕ್ಕೆ ಅವ್ರು ಇದನ್ನ ಗವರ್ಮೆಂಟ್ ಕೊಡ್ಲದ್ರು
ಎಲ್ಲ ಅಲ್ಲಿ ಓದ್ದವರೇ ಕೊಡ್ತಾರಂತ ಅವ್ರಿಗೆ, ಡೋನರ್ಸ್. 53
ಅಲ್ಲ, ನಮ್ಮ ನಂದನ್ ಇನ್ಫೋಸಿಸ್ ನಂದನ್ ಅವರು MITಗೆ $100 million ಕೊಟ್ಟರು ಡೊನೇಷನ್. ಅವರೇ ಅಂದ್ರೆ ಮತ್ತೆ ಹಿಂಗೆ ಎಷ್ಟು ಮಂದಿ ಕೊಡೋರು ಅದಾರ ಅಲ್ಲ. ಇಲ್ಲಿ ಹೆಂಗೆ ಬರೋದು ಅಂತಂದ್ರೆ, ಇಲ್ಲಿ ಒಂದು ಕ್ವಾಂಟಮ್ ಸ್ಪೇಸ್ ಅಂತೇಳಿ ಒಂದು ಅಷ್ಟು ದೊಡ್ಡದೇನಿಲ್ಲ ಬಿಲ್ಡಿಂಗ್. ಎಷ್ಟು ಮಂದಿ 1,000 2,000 ಅದಾರ, 10,000 ಮಂದಿ ಅದಾರ ವರ್ಕರ್ಸ್. ಅಷ್ಟು ಭಾಳ ದೊಡ್ಡದೇನು ಅನ್ಸೋದಿಲ್ಲ. ಅದರ ಇವಾಗ ಹೋದ ವರ್ಷ $17,000 ಕೋಟಿ ರೂಪಾಯಿ, ಅಂದ್ರೆ $2 billion ಅಂತ, $17,000 ಕೋಟಿ ರೂಪಾಯಿ ಅತಗ ಇದು ಬಂದದ್ರಿ ಎಕ್ಸ್ಟ್ರಾ ರೊಕ್ಕ, ಅಂದ್ರೆ ಡಿವಿಡೆಂಡ್ ಟೈಪ್ ಕೊಟ್ರು. ಅತಗ ನೀನು ಇಷ್ಟು ಬಿಸ್ನೆಸ್ ಮಾಡಿದ್ರಂದ್ರೆ ಇಷ್ಟು ಇದು ಕೊಡ್ತೀವಿ, ಇಷ್ಟು ಪರ್ಸೆಂಟೇಜ್ ಕೊಡ್ತೀವಿ ಅಂತ ಹೇಳಿದ್ರಂತ. $40 billion ಬಿಸ್ನೆಸ್ ಮಾಡ್ಯಾನ, 5% ಅಂದ್ರೆ $2 billion ಇದು ಕೊಟ್ರ ಅತಗ ಇನ್ಸೆಂಟಿವ್. ಅಂದ್ರೆ 17,000 ಕೋಟಿ ಇನ್ಸೆಂಟಿವ್ ಒಂದು ವರ್ಷಕ್ಕೆ ಒಬ್ಬ ಮನುಷ್ಯನಿಗೆ ಬಂತಂದ್ರೆ ಲೆಕ್ಕ ಹಾಕಿಲ್ಲ ಎಷ್ಟು ಮನಿ ಇರ್ಬೋದು.
ಒಂದು ಕರೆಕ್ಷನ್, ಅದು 53 ಬಿಲಿಯನ್ ಎಂಡೋಮೆಂಟ್ಸ್ ಅಂತಾರೆ. ಎಂಡೋಮೆಂಟ್ಸ್ ವರ್ತ್ 53 ಬಿಲಿಯನ್.
ಯಾಕೆಂದ್ರೆ ಅದು ಏನೋ ತಪ್ಪಿತ್ತು, ಅವ್ರ ಸ್ಟೇಟ್ಮೆಂಟ್ ಫ್ರಮ್ ಡೋನರ್ಸ್ ಅಂತ ಹೇಳಿದ್ರು, ಅದಕ್ಕೆ
ಇನ್ನೊಂದ್ರೆ ಇವರೆಲ್ಲ ರಿಸರ್ಚ್ನೆಲ್ಲ ಇದಾರಲ್ಲ, ಅವರು ಪೇಟೆಂಟ್ಸ್ ಇದೆ, ಅವ್ರು ಸಾಕಷ್ಟು ದುಡ್ಡು ಬರ್ತಿರ್ತಾರೆ. ಈಗ ನೋಡ್ರಿ, ಅದೇ ಇದನ್ನ ಇವ್ರು ಹೇಳಿದೆ, ಇವರು ಈ ಸೋಲಾರ್ ಸೆಲ್ದು ಹೇಳಿದೆ ನಿಮಗೆ. ಆಮೇಲೆ ಇವನ್ ಲಿಥಿಯಂ ಬ್ಯಾಟ್ರಿ ಬಗ್ಗೆ ಸಹಿತ ಅವರು ಒಳ್ಳೆ ವರ್ಕ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ. ಹೆಂಗೆ ಎಫಿಷಿಯೆಂಟ್ ಆಗಿ ಅದನ್ನ ಎನರ್ಜಿ ಸ್ಟೋರೇಜು ಮತ್ತು ಫಾಸ್ಟ್ ಚಾರ್ಜ್ ಮಾಡೋದು, ಬೋತ್ ಎಫೆಕ್ಟ್ ಸ್ಟಡಿ ಮಾಡ್ತಾ ಇದ್ದಾರೆ. ಅದು ಅಚೀವ್ ಆಯ್ತಪ್ಪ ಅಂತಂದ್ರೆ ಅವ್ರು ಆಟೋಮೆಟಿಕ್ಲಿ ಯಾವುದೋ ಒಂದು ಕಂಪ್ನಿ ಜೊತೆಗೆ ಇದ್ರ ಮಾಡ್ತಾರೆ, ದೇ ಗೆಟ್ ಲಾಟ್ ಆಫ್ ಮನಿ. ಇಟ್ಟು ಹಂಗೆ ಅವರೇ ಜನರೇಟ್ ಮಾಡೋದು ಭಾಳ ಇದೆ ಇಲ್ಲೆಲ್ಲ.
ನೆಕ್ಸ್ಟ್ ಕ್ವಶನ್ ಹೋಗೋಣ.
ಒಂದು ಸ್ಮಾಲ್ ಕ್ವಶನ್ ಹೇಳ ಸರ್, ಕೇಳ ಸರ್, ಒಂದೇ ಸ್ಮಾಲ್ ಕರೆಕ್ಷನ್. ಈ ಲೀನಿಯರ್ ಆಕ್ಸಿಲರೇಟರ್ ನಲ್ಲಿ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಚಾರ್ಜ್ ಆಕ್ಸಿಲರೇಟ್ ಮಾಡಿದಾಗ ವಿಲ್ ಅಪ್ಲೈ ಕರೆಕ್ಷನ್ ಫಾರ್ ರಿಲೇಟಿವಿಸ್ಟಿಕ್ ವೇರಿಯೇಷನ್ ಆಲ್ಸೋ ಆಫ್ ಮಾಸ್.
ಅಲ್ಲ ಅದು ನ್ಯಾಚುರಲ್ ಸರ್. ದೊಡ್ಡ ಈಗ ವೆನ್ ದಿ ಅಲ್ಟಿಮೇಟ್ಲಿ 17 ಗಿಗಾ ಎಲೆಕ್ಟ್ರಾನ್ ವೋಲ್ಟ್ ಎನರ್ಜಿ ಆಗ್ತದೆ ಅಂತಂದ್ರೆ ನ್ಯಾಚುರಲ್ ಅದ್ರ ಮಾಸ್ ಸಿಕ್ಕಾಪಟ್ಟಿರ್ತದಲ್ಲ. ಬಿಕಾಸ್ ಇಟ್ಸ್ ವೆಲಾಸಿಟಿ ಈಸ್ 0.99999 ಟೈಮ್ಸ್ ದ ವೆಲಾಸಿಟಿ ಆಫ್ ನ್ಯಾಚುರಲಿ ಮಾಸ್ ರಿಲೇಟಿವಿಸ್ಟಿಕ್ ಮಾಸ್ ಸಿಕ್ಕಾಪಟ್ಟೆ ಆಗೇ ಆಗ್ತದೆ ಸರ್. ಅದು ನ್ಯಾಚುರಲ್. ಅದು ಎಷ್ಟು ಅಲ್ಲಿ ಒಂತಲ್ಲಿ ಇದು ಇತ್ರಿ, ಅಷ್ಟು ಟೈಮ್ಸ್ ಇದು ಪವರ್ಫುಲ್ ಆಗುತ್ತೆ. ಅದೇ
ಇನ್ನೊಂದು ನೀವು ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಪಾಸಿಟ್ರಾನ್ ಬಗ್ಗೆ ಹೇಳಿದ್ರಿ. ನನ್ನ ಸಿಂಪಲ್ ಕ್ವಶನ್ ಇದೆ, ಇವನ್ ಅಷ್ಟು ನಂಬರ್ ವಾಲ್ಯೂಮ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಹೆಂಗ್ ಜನರೇಟ್ ಮಾಡ್ತಾರೆ? ವಾಟ್ ಇಸ್ ಸೋರ್ಸ್? ಯಾವ ರೀತಿ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ತಯಾರು ಮಾಡ್ತಾರೆ ಅಲ್ಲಿ?
ಎಲೆಕ್ಟ್ರಾನ್ ಗನ್ ಸರ್. ಎಲೆಕ್ಟ್ರಾನ್ ಗನ್ ದೇ ಎಮಿಟ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಇನ್ ದ ಸ್ಟಾರ್ಟಿಂಗ್ ಪಾಯಿಂಟ್.
ವೆರಿ ಸ್ಟ್ರಾಂಗ್ ಗನ್ಸ್ ಇರ್ಬೇಕಲ್ಲ, ಹೈ ಇಂಟೆನ್ಸಿಟಿ ಗನ್ಸ್. ಹೌದಾ?
ಎಲೆಕ್ಟ್ರಾನ್ ಎನಿ ಫೋಟೋ ಸೆನ್ಸಿಟಿವ್ ಮಟೀರಿಯಲ್ ಇಸ್ ಸಫಿಷಿಯಂಟ್ ಟು ಪ್ರೊಡ್ಯೂಸ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಅಲ್ಲ ಸರ್.
ಸ್ಮಾಲ್ ಸ್ಕೇಲ್ ಅಲ್ಲಿ ಸಪೋಸ್ ಯು ವಾಂಟ್ ಫಾರ್ ಆಕ್ಸಲರೇಟರ್ ಅಂದ್ರೆ ಹೈ ಇಂಟೆನ್ಸಿಟಿ ಬೇಕಲ್ಲ, ವೆರಿ ಲಾರ್ಜ್ ನಂಬರ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಪರ್ ಯೂನಿಟ್, ಹೈ ಇಂಟೆನ್ಸಿಟಿ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಬೇಕಾಗುತ್ತೆ. ನಾಟ್ ಓನ್ಲಿ
ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಅವು ಆರ್ಡಿನರಿ ಇದ್ರು ಸಾಕು, ಆಟೋಮೆಟಿಕ್ಲಿ ದೇ ಗೇನ್ ಎನರ್ಜಿ ವೆನ್ ದೇ ಕಮ್ ಔಟ್ ಅಲ್ರಿ.
ಅಯೋನೈಸ್ ಮಾಡ್ಬೇಕಲ್ಲ. ಫಸ್ಟ್ ಯು ಹ್ಯಾವ್ ಟು ಹ್ಯಾವ್ ಅಯೋನೈಸ್ ಆಟಮ್ಸ್ ಅಂಡ್ ಎಲೆಕ್ಟ್ರಾನ್, ದೆನ್ accelerate them ಅಲ್ವಾ?
use on thermionic electrons also.
ಅದನ್ನ ಅವ್ರು ಏನ್ ಮಾಡ್ತಾ ಇದಾರೆ ಅಂತ ಕೇಳ್ದೆ. ಲ್ಯಾಬ್ ವೈಸ್ ಮಾಡ್ತಾ
ಅಲ್ಲ ನಿಮ್ಗೆ ಹೇಳ್ಬೇಕಂತ ಸರ್, ನಮ್ಗೆ ಆ ಎಂಡ್ ಫಸ್ಟ್ ಪಾಯಿಂಟ್ ಕರ್ಕೊಂಡು ಹೋಗ್ಲಿಲ್ಲ, ಲಾಸ್ಟ್ ಪಾಯಿಂಟ್ನಾಗ ಒಂದಿಷ್ಟು ಆ LCLS ಇದ್ರ ತಲೆ ಒಂದೆರಡು ತಲೆ ಕರ್ಕೊಂಡು ಹೋಗಿ ತೋರಿಸ್ತಾರೆ ಹೊರ್ತು ಫಸ್ಟ್ ಪಾಯಿಂಟ್ ಕರ್ಕೊಂಡು ಫಸ್ಟ್ ಪಾಯಿಂಟ್ 3.2 ಕಿಲೋಮೀಟರ್ ಎಂಡ್ಗೆ ಅಲ್ಲಿ ಕರ್ಕೊಂಡು ಹೋಗ್ಲಿಲ್ಲ ಸರ್ ಅವ್ರು.
ಮಾಡ್ಬೇಕು ಆಟಮ್ಸ್ ಅನ್ನ ತಗೊಂಡು.
ಅದ ಹೇಳಿದ್ನಲ್ಲ, ನಾವು ಸ್ಟೂಡೆಂಟ್ಸ್ ಅಂತ ಹೇಳಿ ಹೋದ್ರಂತಂದ್ರೆ ಮೋಸ್ಟ್ ಪ್ರಾಬಬ್ಲಿ ಅಲ್ಲೇ ಇದು ಇರ್ಬೋದು ಅನ್ಸರ್. ಸ್ಟೂಡೆಂಟ್ಸ್ ಇದು ರಿಸರ್ಚರ್ಸ್ ಅಂತಂದ್ರೆ
ಮತ್ತೇನಾದ್ರು ಕ್ವಶನ್ಸ್ ಇದ್ರೆ ಕೇಳ್ಬೋದು.
ಹೇಳ್ರಿ ಸರ್.
ಕೆಣೆದವ್ರ ಅಲ್ಲಿ ಒಂದಿಷ್ಟು ಪಾಂಪ್ಲೆಂಟ್ ಲಿಟ್ರೇಚರ್ ತರಬೇಕು.
ತಂದಿನಪ್ಪ
ಆಗ್ಲೇ ಸರ್ ಕೇಳಿದಕ್ಕೆ ಅದ್ರೊಳಗೆ ಆನ್ಸರ್ ಇರ್ತದ.
ರಾಯಚೂರು ಬಂದ್ರೆ ಕೊಡ್ತಾರೆ, ನೀವು ರಾಯಚೂರು ಬರ್ಬೇಕು.
ಅಲ್ಲ ಬಟ್ ಏನು ಬೇಕಾಗಿಲ್ಲ. ಇನ್ನೊಂದು ಹೇಳ್ತೇನೆ ನಾನು, ಅವ್ರ ವೆಬ್ಸೈಟ್ ಇಷ್ಟು ಡೀಟೇಲ್ಸ್ ಅದಾವ. ಆಮೇಲೆ ಅಂತಂದ್ರೆ ಅವ್ರು ಎಲ್ಲದಕ್ಕೂ ಪ್ರತಿಯೊಂದಕ್ಕೂ ಇದು ಮಾಡ್ಯಾರ, ಯೂಟ್ಯೂಬ್ ನಲ್ಲಿ ಅದಾವ, ಎಲ್ಲ ಅದಾವ. ನೋಡೋದಕ್ಕೆ ಟೈಮ್ ಎಲ್ಲ ಸಿಗ್ತದೆ ನೋಡ್ರಿ. ಎವ್ರಿಥಿಂಗ್ ದೇ ಪುಟ್ ಇದು ಇದರಲ್ಲಿ ವೆಬ್ಸೈಟ್ ನಲ್ಲಿ ಇದೆ, ಅವ್ರ ವೆಬ್ಸೈಟ್ ನಲ್ಲಿ ಇದೆ, ಮತ್ತು ಯೂಟ್ಯೂಬ್ ನಲ್ಲಿ ಬರುತ್ತೆ.
ಇಲ್ಲ ಕೆಣೆದವ್ರ ಎಲ್ಲಾ ವೆಬ್ಸೈಟ್ ನಾಗ ಲಿಟ್ರೇಚರ್ ಇದ್ದಿದ್ ಕೊಡ್ತಾರ, ಟೆಕ್ನಿಕಲ್ ಯಾರು ಕೊಡೋದಿಲ್ಲ. ಅದ್ರೊಳಗ ಅಮೇರಿಕಾದವ್ರಂತೂ ಮೊದಲು ಕೊಡೋದಿಲ್ಲ.
ಹಂಗಲ್ಲಪ್ಪ, ಬಹಳಷ್ಟು
ಯಾಕಂದ್ರ ನಿಮ್ಗೆ ಇಂಡಿಯನ್ ಪಾಸ್ಪೋರ್ಟ್ ಇತ್ತಂದ್ರ ನೀವು ನ್ಯೂಕ್ಲಿಯರ್ ಸ್ಪೆಷಲ್ ಲೆಕ್ಚರ್ ಇದ್ರು ಒಳಗ್ ಬಿಡ್ಬೇಕಾದ್ರೆ ಬಹಳ ಸಲ ವಿಚಾರ ಮಾಡ್ತಾರ. ನೀರೇ ಇಂಡಿಯನ್ ಪಾಸ್ಪೋರ್ಟ್ ಮೇಲೆ ಹೋಗಿದಿ, ಆ ಮೇನ್ ಪಾಯಿಂಟ್ ಯಾಕೆ ಕರ್ಕೊಂಡ್ ಹೋಗ್ತಾರ ಅವರು?
ಎಲ್ಲಾ ಕಡೆ
ಇಲ್ಲ ನಮ್ದಂತಲ್ಲ, ಇದು ಜನರಲ್ ವಿಸಿಟರ್ ಅಲ್ಲ. ಹಿಂಗಾಗಿ ಈ ಜನರಲ್ ವಿಸಿಟರ್ ಎಲ್ಲ ಮಂದಿ ಬಹಳ ಜನ ಇದಿರ್ತಾರಲ್ಲ, ಅಷ್ಟು ಒಂದ್ ಬಸ್ ನಲ್ಲಿ ಸುಮಾರು ನಾವು 16-18 ಮಂದಿ ಇದ್ವಿ ಅಷ್ಟೇ ನಾವು.
ಇದು ಎಲ್ಲಾ ದೇಶದಲ್ಲೂ ಇದ್ದೇ ಇರ್ತಾರೆ.
ನಮ್ಮಲ್ಲಿ
ಸೆನ್ಸಿಟಿವ್ ಫೆಸಿಲಿಟಿ ಇದ್ರೆ ಅವರು ದೇ ಹ್ಯಾವ್ ಟು ಟೇಕ್ ಪ್ರಿಕಾಷನ್ಸ್.
ಅಲ್ಲ ಜೋಗಂದಿ BRC ನೀನ್ ವರ್ಕ್ ಮಾಡಿದಾಗ ಎಲ್ಲೆಲ್ಲ ಅಡ್ಡಾಡಿರ್ತಿದ್ದೆ ಅಲ್ಲೆಲ್ಲ ಈ ಕಡೆವರೆಗೂ
ಸೆನ್ಸಿಟಿವ್ ಹೈ ಸೆಕ್ಯೂರಿಟಿ ಏರಿಯಾಸ್ ಎಲ್ಲ ಕಡೆ ಬಿಡೋದಿಲ್ಲ. ಓಕೆ, ನೆಕ್ಸ್ಟ್ ಕ್ವಶನ್ಸ್
ಸರ್. ಈಗ ಇನ್ನೊಂದು ಅಲ್ಲಿ ಹೇಳಿದ್ರಿ 36 ಬಿಲಿಯನ್ ಡಿಗ್ರೀಸ್ ಫ್ಯಾರನ್ಹೀಟ್ ಅಂತ ಒಂದು ಹೇಳಿದ್ರೆ, ಆ ಟೆಂಪರೇಚರ್ ನ ಹೇಗೆ ಅವರು ಅಚೀವ್ ಮಾಡ್ತಾರೆ, ಏನಾದ್ರು ಐಡಿಯಾ ಇದೆಯಾ ಸರ್?
ಅಲ್ಲ
36 ಬಿಲಿಯನ್ ಅಂದ್ರೆ ಒಂದು
ಸರ್ ಒಂದ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ ನಲ್ಲಿ ಒಂದ್ ಇದ್ರಲ್ಲಿ ಅಲ್ಲಿ ಅಷ್ಟು ಇದು ಇರುತ್ತೆ ಅಂತ ಹೇಳ್ತಾರೆ ಅಷ್ಟೇ. ಅಷ್ಟು ಪವರು ಅಷ್ಟು ಇದ್ದು ಆ ಪರ್ಟಿಕ್ಯುಲರ್ ಪಾಯಿಂಟ್ ನಲ್ಲಿ ಇರುತ್ತೆ ಅಂತ, ನಾಟ್ ಕಂಪ್ಲೀಟ್ ಅದು ಸ್ಪ್ರೆಡ್ ಆಯ್ತಂತ. ಈಗ ನೋಡ್ರಿ ಹೊಸದಾಗಿ ಅದ್ರದ್ದು ಎನರ್ಜಿ ಜಾಸ್ತಿ ಮಾಡೋಕೆ, ಎಲೆಕ್ಟ್ರಾನ್ ಎನರ್ಜಿ ಜಾಸ್ತಿ ಮಾಡೋಕೆ ಇನ್ನು ಎಕ್ಸ್ರೇಸ್ ಸ್ಟ್ರಾಂಗ್ ಮಾಡ್ಬೇಕಂತೇಳಿ ಸೂಪರ್ ಕಂಡಕ್ಟರ್ ಯೂಸ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ ಈಗ ಅವ್ರು. ಯಾಕಂದ್ರೆ ಇನಿಷಿಯಲ್ ಎಲೆಕ್ಟ್ರಾನ್ ಎನರ್ಜಿ ಲಾಸ್ ಆಗಬಾರ್ದಲ್ರಿ. ಮೊದಲು 0.9994 ಟೈಮ್ಸ್ ಇತ್ತಂತ, ನಾವು ದೇ ಮೇಡ್ ಇಟ್ 6 ಟೈಮ್ಸ್. ಅಷ್ಟು ಜಾಸ್ತಿ ಇದು ಇದೆ.
ಟೆಂಪರೇಚರ್ ಹೆಂಗ್ ಬರುತ್ತೆ ಅಂದ್ರೆ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಈಕ್ವಲೆಂಟ್ ಟು KT ಅವು ಮಾಡಿದಾಗ ಎಫೆಕ್ಟಿವ್ ಟೆಂಪರೇಚರ್ ಬರುತ್ತೆ. ಎಲೆಕ್ಟ್ರಾನ್ ಎನರ್ಜಿ ಕಂಪ್ಲೀಟ್ ಡಿಸಿಪೇಟ್ ಆದಾಗ ಎಷ್ಟು ಟೆಂಪರೇಚರ್ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡುತ್ತೆ? ಈಕ್ವಲೆಂಟ್ 1/2 KT = 1/2 MB² ಮಾಡಿದಾಗ ಅದು ಈಕ್ವಲೆಂಟ್ ಟೆಂಪರೇಚರ್ ಆಫ್ ದ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಅಷ್ಟೇ ಅಂತ ಅನ್ಸೋದು ನನಗೆ. ಓಕೆ, ಮತ್ತೇನಾದ್ರು ಪ್ರಶ್ನೆಗಳಿದ್ದ ಕೇಳ್ಬೋದು. ಅವ್ರು ಹೇಗಿತ್ತು ಬರ್ತಾರಲ್ಲ ವಾಪಸ್ ಬಂದಾಗ ಬೇಕಾದ್ರೆ ಇನ್ನೊಂದು ಆಫ್ಲೈನ್ ಪ್ರೆಸೆಂಟೇಶನ್ ಬೇಕಾದ್ರೆ ಇಟ್ಕೋಬಹುದು.
ಅಲ್ಲ ಅಲ್ಲ ಪ್ರೆಸೆಂಟೇಶನ್ ನಾವು ಎಕ್ಸ್ಪೋರ್ಟ್ ಮಾಡಿದ್ರೆ ಬರುತ್ತೆ, ಇದನ್ನೇ ತೋರ್ಸ್ಬೇಕಾಗ್ತದೆ ಅಷ್ಟೇ. ಅವ್ರು ಮಾಡಿದ್ ಹೇಳ್ಬೇಕು.
ಅಲ್ಲ ಇವೆಲ್ಲಾ ಕ್ವಶನ್ಗಳಿಗೆ ಆನ್ಸರ್ ಇನ್ನೊಂದ್ಸಲ ವಿಸಿಟ್ ಮಾಡ್ಕೊಂಬಲ್ರಿ, ಆಮೇಲೆ ಇಡೋಣ ಅಂತ.
ಅಲ್ಲ ಹೇಳಿದ್ನಲ್ಲೋ, ಇನ್ನೊಂದ್ಸಲ ವಿಸಿಟ್ ಮಾಡಕ್ ಹಂಗ ನೀನ್ ಇದಕ್ ಕೊಡೋದಲ್ಲ. ನಿಂದು ಇದಕ್ ಕೇಳ್ತಾರ, ನೀ ಎಲ್ಲಿ ವರ್ಕ್ ಮಾಡ್ತೆ ಅಂತ ಕೇಳ್ತಾರ, ಏನ್ ಕೊಡ್ಬೇಕು, ರಿಟೈರ್ಡ್ ಅಂತ ಹೇಳಿದ್ರೆ ನಡೆಯಂಗಿಲ್ಲಪ್ಪ.
Sir, you can visit other centers also because you are in USA.
ಎಸ್ ಮಾಡಿದ್ದೀನಿ ಸರ್, ನಾನು ಅದೇ ಹೇಳಿದ್ನಲ್ಲ, ಬೇರೆ ಬೇರೆ ಯೂನಿವರ್ಸಿಟಿಗಳೆಲ್ಲ ಹೋಗಿ ಬಂದಿದ್ದೀನಿ.
Brief about other centers. The next talk.
ಅಲ್ಲಲ್ಲ ಇದು ಸುಮ್ಮನೆ ಅದು ಅಲ್ಲೇ ನೋಡಿದ್ದ, ಅದು ಯೂನಿವರ್ಸಿಟಿ ನೋಡಿದ, ಬಿಲ್ಡಿಂಗ್ ನೋಡಿದೆ, ಲೈಬ್ರರಿ ನೋಡಿದೆ, ಅದಂತ ಹೇಳ್ಬೇಕಾಗತ್ತೆ. ಯಾಕಂತಂದ್ರ ಇನ್ನೊಂದು ಹೇಳ್ತೀನಿ ರೀ, ಲ್ಯಾಬೊರೇಟರಿ ಒಳಗೆ ಬಿಡಂಗಿಲ್ಲ. ಲ್ಯಾಬೊರೇಟರಿ ಅದ್ರಾಗ ನಮ್ದು ಏನಾಯ್ತಂದ್ರೆ ಇತ್ತೀಚೆಗೆ ಈ ಕರೋನಾ ಪೀರಿಯಡ್ ಬಂತಲ್ರಿ, ಈ ಕರೋನಾ ಪೀರಿಯಡ್ದಾಗ್ಲಿಂದಂತೂ ಎಲ್ಲೂ ಬಿಡ್ತಾ ಇಲ್ಲ ಯಾರನ್ನು. ಪ್ಲಸ್ ಮೊದಲಿಂದನೂ ಅವ್ರದ್ದು ಐಡೆಂಟಿಟಿ ಕಾರ್ಡ್ ಇರಬೇಕು, ಅದನ್ನ ನೀವು ಅದನ್ನ ತೋರಿಸ್ಬೇಕು, ಒಳಗೆ ಗೇಟ್ ವಿಲ್ ಓಪನ್, ನೀವು ವಿಲ್ ಎಂಟರ್, ಅದರ್ವೈಸ್ ನೋ. ಇವನ್ ಇಲ್ಲೊಂದು ಸ್ಕೂಲ್ಗೆ ಹೋಗ್ಬೇಕಂತಂದ್ರೆ ಅಲ್ಲಿ ಅವ್ರು ಇದನ್ನ ಮಾಡಿದ್ರೆ, ಮೊದಲು ನಿಮ್ಮ ಇದು ಕಳಿಸ್ರಿ ಅಂತ ಕೇಳಿದ್ರೆ ನನಗೆ, ಬಯೋಡಾಟಾ ಕಳಿಸ್ರಿ, ನೀವು ಎದಕ್ಕೆ ಬರ್ತಾಯಿದ್ರಿ ಕಳಿಸಿ, ನಿಮ್ಮ ಟಿ ವಿ ಕಳಿಸಿ ನೋಡಿ, ಆಮೇಲೆ ಅವರು ದೇ ವಿಲ್ ಸೇ ಸ್ಕೂಲಲ್ಲಿ ನೀವು ಬರ್ಬೇಕಾ ಬರಬಾರ್ದ, ಒಳಗೆ ಬಿಡ್ಬೇಕಾ ಬಿಡಬಾರ್ದು ನಿಮ್ಮನ್ನಂತ.
ಮತ್ತೇನಾದ್ರು ಕ್ವಶನ್ಸ್ ಇಲ್ಲಿ ಇದ್ರೆ ಪ್ರೊಫೆಸರ್ ನಾಗರಾಜ್ ಅವರು ವೋಟ್ ಆಫ್ ಥ್ಯಾಂಕ್ಸ್.
ತುಂಬಾ ಧನ್ಯವಾದಗಳು ಸರ್, ಯಾಕಂದ್ರೆ ಸಾಕಷ್ಟು ಡೇಟಾನ ಕಲೆಕ್ಟ್ ಮಾಡಿದೀರಾ. ಯಾಕೆಂದ್ರೆ ನೀವು ಅದರಲ್ಲಿ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಮಾಡದೇ ಇದ್ರು ಮಾಡಿರೋ ತರನೇ ಒಂದಷ್ಟು ಡೇಟಾ ಕಲೆಕ್ಟ್ ಮಾಡಿ ನಮ್ಗೆಲ್ಲ ಹೇಳಿದೀರಾ. ಸ್ಲಾಕ್ಗೆ ನಮ್ಮನ್ನೆಲ್ಲ ಕರ್ಕೊಂಡು ಹೋಗಿದ್ರಿ, ಹಾಗಾಗಿ ನಿಮ್ಗೆ KPA ಕಡೆಯಿಂದ ಧನ್ಯವಾದಗಳು. ಅದರ ಜೊತೆಗೆ ಈ ಪ್ಲಾಟ್ಫಾರ್ಮ್ನ, ಝೂಮ್ ಪ್ಲಾಟ್ಫಾರ್ಮ್ನ ನಮ್ಗೆ ಪ್ರತಿ ಸಂಡೇನು ಕೊಡ್ತಾ ಇರುವಂತ ಡಾಕ್ಟರ್ MK ರಾಘವೇಂದ್ರ ಅವ್ರಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು. ಕಾಗ್ಲಿ ಅವರು ಎಡಬಿಡದೆ ಹಾಗೂ ಕಷ್ಟಪಟ್ಟು ಎಲ್ಲರನ್ನು ಹಿಡಿದು ಈ ಒಂದು ಟಾಕ್ ಅನ್ನು ಅರೇಂಜ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ. ಹಾಗಾಗಿ ಅವ್ರಿಗೆ ಮತ್ತೆ ನಮ್ಮ ಎಲ್ಲ KPA ರಾಮನ್ ಅವರು ಯೂಟ್ಯೂಬ್ ಅನ್ನ ಮಾಡ್ತಾ ಇದ್ದಾರೆ, ಅವ್ರಿಗೋಸ್ಕರ. ಮತ್ತೆ
ರಾಮನ್ ಅವ್ರು ಇದಾರೆ ಇದ್ರಲ್ಲಿ,
SV ರಾಮನ್ ಅಂತ
ಅಲ್ಲ ಈ ಮೀಟಿಂಗ್ ಅಲ್ಲಿ ಇದಾರೆ ಅವರು. ಸರ್ ಒಂದು ಟೈಮ್ ನಮ್ಮ ಆಶ್ರಿತ್ ಅವರು ಒಂದು ಟಾಕ್ ಕೊಟ್ರು 13th
ಲಾಸ್ಟ್ ಸಂಡೇ.
ರಾಮನ್ ಯು ಆರ್ ಅವೈಲಬಲ್?
ರಾಮನ್ ಅವರೇ, ಅವರು ಆಶ್ರಿತ್ ಅವ್ರಿಗೆ ಅವ್ರದ್ದು ರೆಕಾರ್ಡೆಡ್ ಏನಾದ್ರು ಅದು ಯೂಟ್ಯೂಬ್ ನಲ್ಲಿ ಎಲ್ಲಿ ಸಿಗ್ತದೆ ಏನಾದ್ರು ನಮ್ಗೆ ಸ್ವಲ್ಪ ಕಳಿಸ್ತೀರ?
That is unfortunately what happened last week. There is a signal issue, sir. Then nearby it was not recorded properly. I'll try to make it, sir.
Yes.
Okay, sir. So ಮತ್ತೊಮ್ಮೆ ನಿಮ್ಗೆ ಮತ್ತೆ ಎಲ್ರಿಗೂ ಧನ್ಯವಾದಗಳು. ಹಾಗೇನೆ ವಿಜಯರಾವ್ ಅನ್ನೋರೊಬ್ರು ಅಟೆಂಡ್ ಮಾಡಿದ್ರು, ಜೊತೆಗೆ ಇನ್ನೂ ಕೆಲವರು ಅಟೆಂಡ್ ಮಾಡಿದ್ರು. ಅವ್ರನ್ನು ಎಲ್ಲ ನಾವು ನಮ್ಮ KPA ಮೆಂಬರ್ ಆಗಿ ಅಂತ ರಿಕ್ವೆಸ್ಟ್ ಮಾಡ್ಕೋತೀವಿ. ಅಂದ್ರೆ ಈ ಅಟೆಂಡ್ ಮಾಡ್ಬೇಕು ಅಂದ್ರೆ ನೀವೆಲ್ಲ ಮೆಂಬರ್ ಆಗ್ಬೇಕು ಅಂತೇನಲ್ಲ, ದಯವಿಟ್ಟು ಮೆಂಬರ್ ಆದ್ರೆ ಇನ್ನೂ ತುಂಬಾ ಒಳ್ಳೇದು. ಜೊತೆಗೆ ಸರ್ ವಿಜಯರಾವ್ ಅನ್ನೋರು ಯಾರು ಅನ್ನೋ ಗೊತ್ತಾಗ್ಲಿಲ್ಲ. ವೀಕ್ ಅಶ್ವಿತ್ ಅವ್ರಿಗೂ ಬಂದಿದ್ರು, ಇವತ್ತು ಅಟೆಂಡ್ ಮಾಡಿದ್ದಾರೆ.
ಆಶ್ರಿತ್ ಜೋಗದು ನಾವು ಎಲ್ಲ ಕ್ಲಾಸ್ಮೇಟ್ಸ್ ನಾವು, ಹಿಂಗಾಗಿ ಅವ್ರು ಬಂದಾರ ಅಷ್ಟೇ.
ಸೊ ಹಾಗಾಗಿ ಅವರು ಫಿಸಿಕ್ಸ್ ನವ್ರೆ, ಆದ್ರಿಂದ ನೀವು ಹೇಳಿ ಸರ್ ಅವ್ರನ್ನು ನಮ್ಮ KPA ಲೈಫ್ ಮೆಂಬರ್ ಆಗ್ಲಿ. ಮತ್ತೆ ಅವರು ಕೂಡ ಒಂದು ಟಾಕ್ ಅನ್ನ ಕೊಟ್ರೆ ತುಂಬಾನೇ ಸಂತೋಷ. ಸೊ ಬಂದಿದ್ದಂತ ಎಲ್ರಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳು. ಮತ್ತೊಮ್ಮೆ ಮೀಟ್ ಮಾಡೋಣ ಬಹುಶಃ ನೆಕ್ಸ್ಟ್ ಸಂಡೇ ಅಂತ.
ನೆಕ್ಸ್ಟ್ ಸಂಡೇ ಒಂದು ಟಾಕ್ ಇರುತ್ತೆ. ಈಗಾಗಲೇ ಹೇಳ್ತಾ ಇದೀನಿ, ನೆಕ್ಸ್ಟ್ ಸಂಡೇ ಪ್ರೊಫೆಸರ್ ರುದ್ರಸ್ವಾಮಿ ಅವರು he will talk about particle accelerators from the very earliest to the latest, from electron accelerator, from cathode ray tube ಇಂದ ಹಿಡ್ಕೊಂಡು CERN ವರ್ಗೂ different type of accelerators ಇದಾವಲ್ಲ, how they were produced and what are their results ಎಲ್ಲ ಹೇಳ್ಕೊಡ್ತಾರೆ. Please join us next Sunday 11 o'clock ಇರುತ್ತೆ. Please join, all of you are invited to join next Sunday, please.
ಮತ್ತೊಂದು ಸರಿ ಎಲ್ರಿಗೂ ಧನ್ಯವಾದಗಳು ಸರ್.
Okay, thank you. Now we close ಮಾಡ್ತಾ ಇದ್ದೀವಿ. Thank you very much.
Thank you, sir.